Hello everyone, this is Ganavi, studying in Sri Venkateswara College of Engineering, Bangalore, of Department Electronics and Communication, subject Maths, title Rate of Growth and Decay. Now let's get started. Introduction to Growth and Decay. Almost everything in our world grows and decays, from the growth of organisms to their eventual death, from the growth of suns to their eventual supernovas. Sometimes we describe process of growth and decay whether physical, chemical, biological, or mathematical model. One of the most common ways in which a quantity can grow or decay is exponentially. We primarily focus on exponential growth and decay. Differential equation for exponential growth and decay. Consider the equation dx by dt is equal to kx, where t and x are variables and k is a constant with k is not equal to 0. As an equation involving derivatives, this is an example of a differential equation. We often think of t as measuring time and x as measuring some positive quantity over time. That is, x is a function of time. The number k is called continuous growth rate if it is positive, or the continuous decay rate if it is negative. There are many quantities in the real world that approximately obey an equation similar to this one, as we will see shortly. We will first solve the equation in general, taking the reciprocal of both sides and noting via the chain rule that dx by dt into dt by dx is equal to 1 gives dt by dx is equal to 1 by kx. To solve this equation, we integrate 1 by kx. Recall that k is a constant and we are assuming that x is positive, so we obtain t is equal to integral of 1 by kx into dx is equal to 1 by kx into integral of 1 by x dx, which is equal to 1 by k log e x plus c, where c is a constant of integration. Rearranging this equation to express x in terms of t, we have x is equal to e to the power k into t minus c. We can simplify by noting that e to the power k t minus c is equal to e to the power k t minus kc, which is equal to e to the power minus kc into e to the power kt. And the first factor, e to the power minus kc, is just a positive constant which we call c. The general solution to the differential equation is then x into t is equal to c e to the power kt, where c is any positive constant. It's easy to verify that any such function is a solution. Differentiating x is equal to c e to the power kt with respect to t gives k times x. Depending on whether k is positive or negative, the quantity x grows or decays with respect to t, as shown in the following graphs. Non-exponential growth and decay. All the quantities we have seen so far, such as population and radioactive samples, grow or decay exponentially. That is, they are exponential functions of time t. However, many quantities in the world grow or decay in a non-exponential fashion. For instance, the electric field strength E of a charged particle decreases rapidly as you move away from the particle. At a distance r from the particle, the field strength is E is equal to c by r square, where c is a constant. The electric field strength is said to obey an inverse rather than an exponential law. The decay involves r to the power minus 2 rather than e to the power minus r. Many other quantities in the world, such as gravitational force, sound intensity, and radio signal strength, obey inverse square laws. Another interesting example is Zipf's law, which concerns spoken language. Suppose we rank all the words in a language according to their frequency as spoken. Zipf's law states that frequency f in spoken language of the world ranked r is inversely proportional to r, that is, f is equal to c by r for some constant c. In other words, word frequency decreases in inverse proportion to rank. When two quantities x and y are related by an equality of the form y is equal to cx to the power a, where c and alpha are non-zero constants, we say they obey a power law relationship. The examples from this section are all power law relationships: inverse square decay, alpha is equal to minus 2, Zipf's law, alpha is equal to minus 1, linear growth, alpha is equal to 1, quadratic growth, alpha is equal to 2, Exponential growth or decay is not a power law relationship. Examples of growth. A classic example of growth in differential equations is a population model where the rate of population change, represented by the derivative, is directly proportional to the current population size, often written as dp by dt is equal to kp, where p is the population size, t is time, and k is a positive constant representing the growth rate. This essentially means the larger the population, the faster it grows. Other examples of growth in differential equations include bacterial growth, modeling the increase in bacteria count within a culture over time, where the growth rate is proportional to the current bacterial population. Compound interest, calculating the accumulation of money in a bank account where interest is compounded continuously, represented by a differential equation, where the rate of change in the account balance is proportional to the current balance. Radioactive decay. While technically decay, the same differential equation structure can be used to model the decrease in radioactive material over time, where the decay rate is proportional to the remaining amount of the substance. Examples of decay. A classic example of decay in differential equations is modeling the radioactive decay of a substance, where the rate of decay is directly proportional to the amount of substance remaining, represented by the equation dq by dt is equal to minus kq, where q is the quantity of the substance at time t and k is a positive constant representing the decay rate. Other examples of decay in differential equations include population decline, modeling the decrease of a population over time where the rate of decrease is proportional to the population size, cooling of an object, describing the temperature decrease of a hot object as it cools down to ambient temperature, where the rate of cooling is proportional to the temperature difference, drug concentration in the bloodstream, representing how the concentration of a drug in a patient's body decreases over time due to metabolism and excretion. Conclusion. In conclusion, growth and decay refers to the mathematical concept of a quantity either increasing growth or decreasing decay over time, often following an exponential pattern where the rate of change is proportional to the current value, with applications in various real world scenarios like population dynamics, radioactive decay, and compound interest. The key distinction between the two is the direction of change, with growth signifying an increase and decay indicating a decrease.